In the last video, we looked at the oscillations of a spring mass system and derived its frequency and period of oscillation. In this video, we'll do the same for another common oscillation application, that is, the oscillation of a swinging mass or pendulum. Consider the following idealized pendulum consisting of a mass on a light cord. The pendulum is ideal, meaning that it does not have any friction, so once set in motion, it will continue to oscillate indefinitely. The mass is 1 kilogram and the length of the pendulum is 1 meter. In its equilibrium position, the pendulum is hanging vertically downwards and is at rest. This means that the net force acting on it is zero. The mass pulls on the cord and exerts a force equal to the mass's weight. So the cord pulls back with an equal but opposite force, called the tension, along the cord in accordance with Newton's third law. Now let's raise the mass so that the pendulum is at an angle of 60 degrees from the vertical. Then let the mass go. We see that it will swing from side to side in simple harmonic motion. If it is an ideal system where there is no friction, then the pendulum will swing to the same angle on the other side. Let's freeze the motion for the time being and analyze the forces acting on the mass. At all times, we have the force of gravity acting on the mass vertically downwards. The mass pulls at the cord and causes tension in the cord. This tension is required to balance a component of gravity which acts in the direction that is perpendicular to the arc of the oscillation, as well as the centrifugal force at that point in time due to the partial circular motion of the mass. Since the mass is at some angle with respect to the vertical, then the component of gravity that is directed along the length of the cord is given by mg cos theta. Gravity will also have a component that is tangential to the arc of the oscillation, given by mg sin theta. It is this component of the gravitational force that causes the pendulum to swing, since it's the only force that acts in the direction of the swing. This force gets larger the further the mass is displaced from its equilibrium position because the angle becomes larger. And it is zero when the mass is at equilibrium because the angle is zero. So this force varies proportionally with displacement and tries to bring the mass back to its equilibrium position. This is a key characteristic of simple harmonic motion. It is the restoring force in the pendulum. The restoring force is equal to the product of the spring constant and the displacement. In the case of a pendulum, the restoring force comes from the component of gravity that is tangential to the displacement of the swing. When analyzing a simple pendulum, it's convenient to use a small angle approximation. If the angle, when expressed in radians, is small, then sin theta is approximately equal to theta. Click on the link below for an explanation of this approximation. In the limit that the angle is small, the restoring force is equal to the product of the mass with gravity and the angle. The mass is displaced from its equilibrium a distance that is equal to the arc length of a circle through an angle theta. The arc length is defined as a product of the angle of the arc and its radius. In this case, the radius is the length of the pendulum. From this, we get the angle being equal to the displacement divided by the pendulum length. Substituting this into our restoring force equation gives mgx divided by L being equal to kx. Eliminating the displacement x on both sides of the equation leaves the spring constant being equal to mg divided by L. So the spring constant of the pendulum, or swinging mass, is equal to the weight of the mass divided by the length of the pendulum. From the previous video, we've derived the frequency for a simple harmonic oscillator to be 1 over 2 pi times the square root of the spring constant divided by the mass. If we now substitute the spring constant for a pendulum into this equation, we get the following. The masses cancel out, leaving just gravity divided by the length under the square root. So the frequency of oscillation for a pendulum is proportional to the acceleration due to gravity and inversely proportional to its length. And of course, the frequency is equal to the inverse of the period of oscillation. So the period must be equal to 2 pi times the square root of the length divided by the acceleration due to gravity. Knowing the period or the frequency of oscillation allows us to predict the motion of the swinging pendulum by utilizing the acceleration, velocity, and displacement equations derived in the earlier video. So for this pendulum, which has a mass of 1 kilogram attached to a 1 meter cord, what is the frequency of oscillation? And what is the period of oscillation? In summary, the frequency of a pendulum is equal to 1 over 2 pi times the square root of the acceleration due to gravity divided by the length of the pendulum. The period of oscillation is the inverse of frequency and is equal to 2 pi times the square root of the length of the pendulum divided by the acceleration due to gravity.